Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back to the show. Today we're going to fundamentally change the way you look at the sky.
Yeah, literally. The actual physical sky you see every day.
Right. And I don't mean that in, some kind of metaphorical reach for the stars kind of way. I mean literally. We are talking about the sun.
The sun.
Yeah.
Skull, our local star.
Right. And I know the immediate reaction might be, okay, the sun, it's big, it's hot, it rises in the east, sets in the west, and if I stare at it, I go blind.
Which you should not do.
No, absolutely do not do that. But we tend to take it for granted, I think. It's the background lighting for our lives. But in the world of astronomy, the sun isn't just a light bulb. It is a key, like a literal skeleton key that unlocks the physics of the entire universe.
It really is. It's the Rosetta Stone of astronomy. That's really the core concept we are unpacking today for you. It's the only star in the universe that doesn't look like a dot.
Yeah, and we have a massive stack of research to get through today. This is primarily centering on a major review paper by Shintaro Yomi and his colleagues. And the mission of this exploration today is to understand how scientists are using our sun, the only star we can actually see in high definition, to decode the blurry, pixelated signals we get from every other star in the galaxy.
Exactly. It's really about bridging the gap between solar physics, which is the study of our specific star, and stellar physics, which is the study of all those other points of light. Mm-hmm. Historically, these have been two totally separate fields, but now they are merging.
So let's start with the big picture. You mentioned the problem of distance earlier when we were chatting. I think we need to really settle into this idea to understand why this research is so crucial.
Right. Think about this. When you look up at the night sky, or even when we use our most powerful tools, the James Webb Space Telescope Hubble, those massive ground-based observatories down in Chile, what do we actually see when we look at a star?
I mean, even with the best zoom lenses in human history, we basically just see a dot, a pixel.
Precisely. We call it a point source. We can analyze the light coming from that point. We can break it into a spectrum to see what it's made of. We can measure if it gets brighter or dimmer over time, but we cannot resolve the surface. We can't see the geography.
The actual physical features.
Right. We can't see the storms. We can't see the sunspots or the flares directly. It is just a single pixel of data that contains all that information just meshed together.
It's like trying to understand the complexity of New York City by looking at a single light bulb on the Empire State Building from space.
That's a great analogy. Now compare that to the sun. The sun is close. We can see its eyelashes, practically. We can see sunspots the size of Earth. We can see giant loops of magnetic plasma arching over the surface. We can see solar flares exploding in real time.
It's basically high-definition 4K video of the sun's surface.
Yeah, exactly. So the Rosetta Stone analogy here is all about translation.
Right. Because the original Rosetta Stone allowed us to translate Egyptian hieroglyphs, which were a total mystery, because we had the exact same text written in Greek, which we already understood.
Exactly. The sun is our Greek text. We know what the sun looks like up close. We understand the physics of the surface because we can actually see it happening.
And the hieroglyphs are the distant stars.
Right. We take the HD view of our sun and we mathematically downgrade it. We blur it on purpose. We turn our sun into a single pixel to see what it would look like if it were, 50 light years away.
Oh, wow.
Yeah. And by comparing the HD version, what we absolutely know is happening with the pixel version, the signal we would receive, we learn how to read the signals from other stars.
That is incredibly cool. We are basically training ourselves on the sun so we can play detective with stars that are hundreds of light years away. We're building a dictionary of stellar signals.
That is exactly it. And the primary tool for this investigation, our magnifying glass, if you will, is a spacecraft called the SDO.
NASA's Solar Dynamics Observatory.
Yes. Launched back in 2010. And before we get into the actual results, I think we really need to pause on the SDO itself, because calling it a camera feels like a bit of an insult to the engineering involved.
I agree completely. Reading the specs on this thing, it's an absolute beast.
Yeah.
It's not just taking snapshots for Instagram. It's a suite of 3 very specific, very sophisticated instruments.
It's like having an X-ray machine, an MRI, and a thermal camera, all pointed at the exact same patient simultaneously. It sees the sun in layers.
Okay, let's break down these eyes of the SDO for beginners who might not be familiar, because understanding how they see is crucial to understanding the data we're going to discuss later. So the first one is called HMI.
Right. The helioseismic and magnetic imager. This is the heavy lifter. It's not looking at light in the way your phone camera does. It's specifically measuring the magnetic field at the solar surface.
Now, this brings us to the actual physics of it all. How do you take a picture of a magnetic field? Because magnetic fields are invisible, right?
They are invisible to the naked eye, yes, but they leave a very specific fingerprint on light. It's called the Zeeman effect.
The Zeeman effect. Okay, let's unpack that for everyone.
Sure. Imagine you were looking at a specific color of light emitted by an iron atom on the sun, a spectral line. If that iron atom is just sitting there in a calm, quiet region, that line is sharp and singular. It's just one line.
Okay.
But if you place that iron atom inside a strong magnetic field, like inside a sunspot, that single line splits. It literally divides into 3 distinct lines.
It actually splits the light itself.
It splits. The energy levels of the electrons in the atom are physically shifted by the magnetic field, and the amount of splitting, how far apart those new lines are, tells you exactly how strong the magnet is.
So the HMI instrument is scanning the entire face of the sun millions of times a day, looking for this tiny microscopic splitting of light.
Exactly. And by mapping that splitting, it creates what we call a magnetogram. It's basically a topographic map of the magnetic forces turning on the surface.
That's the engine room. Because as we know, magnetism drives pretty much everything on the sun.
It is the puppet master. Everything interesting, the flares, the spots, the giant eruptions, it all starts with the magnetic field twisting and snapping. HMI gives us the map of those puppet strings.
Okay, so that's the magnetic map. Then we have the glamour shots, the instrument called AIA.
The atmospheric imaging assembly. When you see those stunning, golden, swirling videos of the sun on the news or in documentaries, the ones that look like a living, breathing ball of fire.
Yeah, the ones that make you suddenly realize the sun is actually a terrifying object.
Yeah, that is AIA data. But again, it's not just a standard camera taking a color photo. It specifically filters light to look at extreme temperatures.
This is the part that fascinated me in the Toriumi paper. It's not looking at colors like red or blue. It's looking at ionization states.
Right. It looks at extreme ultraviolet light. At these insane temperatures, atoms literally get stripped of their electrons. We call this ionization. So AIA has a filter that only lets in light from iron atoms that have lost, say, 8 electrons.
And that specific loss only happens at a specific temperature.
Exactly. Iron 9, which is iron that has lost 8 electrons, glows brightest at about 600,000 degrees, but iron 18 might glow at 6 million degrees. So by mechanically switching filters, the AIA can basically peel the onion. It can say, show me only the gas that is exactly 1 million degrees, and suddenly you see specific loops and structures that are completely invisible at other temperatures.
So we have the magnetic map from HMI and the temperature-sliced atmosphere from AIA. And the third one is EVE.
The Extreme Ultraviolet Variability Experiment. Unlike the other two, EVE isn't taking a picture at all. It's an irradiance sensor. It measures the total energy output.
So it's a giant light meter.
A very, very fancy light meter. It tells us exactly how much energy the sun is screaming out into the solar system at any given second across the entire UV spectrum.
So putting it all together for you listening, HMI shows us the cause, which is magnetism.
Right.
AIA shows us the structure, the atmosphere itself, and EVE shows us the output, the actual energy hitting us.
Correct. And here is why SDO is the absolute foundation of this Rosetta Stone project. It has been staring at the sun 24/7 for well over a decade. It never blinks.
That is a staggering amount of data.
It's massive. And crucially, it covers a full solar cycle. The sun breathes, essentially. It has solar maximum, where it is angry, covered in spots, and constantly flaring. And it has a solar minimum, where it is very quiet and virtually blank. SDO captured the entire transition from quiet to angry and back again.
So we have a complete baseline. We know what a chill star looks like, and we know what a raging star looks like in high definition.
Exactly. And that leads us directly to the core methodology of the paper. They call it the sun as a star experiment.
This is the reverse engineering part. Walk us through how they actually performed this experiment.
It's a brilliant synthesis of data. They take those incredible high-resolution images from SDO where you can see the sunspots and the loops perfectly clearly, and they deliberately ruin them.
They ruin them, like blur them out.
They integrate them. They sum up all the light from the entire disk into a single data point. They simulate what the sun would look like if it were a pinpoint of light 50 light years away.
I see. They force the sun to look like a distant star to match the data we get from telescopes.
Right. But, and here's the absolute key, they keep the original HD footage, so now they have a direct link. They can look at the fake star data and say, okay, look at this little dip in the light curve, what caused that? Then they look at the HD map from the same exact moment and say, aha, that dip was caused by this specific group of sunspots rotating across the center.
That is genius. It totally eliminates the guesswork. Instead of just theorizing about what a blip on a distant star means, we have an actual catalog of blips from our own sun to compare it to.
Exactly. It's building a dictionary. And as we move into decoding the light, we find that the translation isn't always as straightforward as we might hope. It turns out stars can be incredibly tricky.
Right, so the paper discusses a specific study by Toriyumi and his team where they watch transit events. Now, for the beginners out there, a transit event just means something moving across the face of the star as it rotates, right?
Yes. The sun rotates roughly once every 27 days. So if a sunspot forms on the left side, it will slowly march across the face to the right side over the course of about 2 weeks.
Let's look at the first case study here, the sunspot. In my head, this is simple. A sunspot is a dark patch on the surface. It's like a dimmer switch. So if a dark patch moves in front of the camera, the total light we receive should drop.
And in visible light, the normal light our eyes can see, that is exactly what happens. When a big sunspot group rotates into view, the total brightness of the sun drops. It creates a measurable dip in the light curve.
Simple physics. You block the light, it gets darker. But the notes say there's a twist here involving something called faculae.
There's always a twist in astrophysics. Faculae. It's Latin for little torches.
Little torches. That actually sounds quite poetic.
It is. Faculae are these bright magnetic regions that usually cluster around sunspots. They are like a glowing network of magnetic cracks in the surface. Now, here is where the geometry gets weird. When a sunspot is right in the middle of the sun, looking straight at us, the dark spot wins. The total light dips. But when that sunspot group is near the edge of the sun, what we call the limb, the faculae actually take over.
Why? Why does the physical position on the sphere matter?
It has to do with something called the hot wall effect.
The hot wall effect. Okay, break that down for us.
Imagine a facula is like a physical depression in the sun's surface, like a magnetic pothole.
Okay, I'm picturing a pothole in the street.
The floor of that pothole is cooler and darker than the surrounding area, but the vertical walls of the pothole are very hot and very bright.
Got it.
If you look straight down into the pothole from above, like when it's perfectly in the center of the sun facing Earth, you mostly just see the cool, dark floor, so it doesn't look very bright to you.
But if I look at it from a severe angle?
Exactly. As it rotates to the edge of the sun, your viewing angle changes drastically. You can no longer see the dark floor of the pothole at all. Your line of sight hits the vertical, glowing hot wall of the canyon. So suddenly, this thing that looked faint or dark becomes incredibly bright.
That is wild. So depending entirely on where the sunspot is located on the sphere, the star as a whole might look dimmer or brighter.
Exactly. When the active region is on the edge, those faculae can actually boost the total brightness so much that they completely cancel out the darkness of the sunspot. So a sunspot signal isn't just a simple dip. It's a very complex dance of dipping and brightening depending on the viewing angle.
That definitely complicates things for astronomers looking at other stars. If you don't know about the hot wall effect, you might completely misinterpret the light data you're receiving.
You absolutely would. You'd think the star was behaving erratically. And it gets even trickier with the second case study, the spotless plage.
Plage, P-L-A-G-E, that's French for beach, right?
Yes, it is. In solar physics, a plage is basically a huge region of magnetic activity, very much like a sunspot group, but without the actual dark spot in the middle. It's just the bright magnetic network spread out over an area.
So it's basically a sunspot ghost. It has all the underlying magnetism, but none of the dark core.
In a way, yes. Now here is the kicker. If you look at a plage in visible light, you barely see it at all, because there is no dark spot to block the light. And that bright magnetic network is just too faint to show up against the overwhelming glare of the rest of the sun. So the visible light curve just stays flat.
So if I'm an alien astronomer looking at our sun with a regular visible light telescope and a massive plage rotates by, I just think the sun is completely quiet.
You'd think it was fast asleep. You'd write in your log, no activity today. But if you switch your telescope to look at ultraviolet light, that exact same plage lights up like a Christmas tree.
It suddenly becomes visible.
It totally dominates the view. In UV, the plage is screaming with activity. This is one of the most important lessons we've learned from the SDO data. Visible light is a terrible, terrible way to measure the true magnetic activity of a star. You might look at a star in visible light and think it's boring and safe, but if you switch to UV, you realize it's actually raging with massive magnetic storms.
That feels like a very important distinction, especially if we're looking for habitable planets around these stars. We'll definitely get to the habitability question later, but this idea that a star can hide its aggression, so to speak, in the UV spectrum is a bit unsettling.
It completely changes how we interpret so-called quiet stars in our galaxy.
I want to talk about another geometric puzzle mentioned in the research, the time lags. This connects back to the three-dimensional structure of the sun.
This is one of my favorite visualizations from the Toriumi paper. It's about fundamentally understanding that the sun isn't a flat disk painted on the sky. It's a sphere, and it has an atmosphere that extends far upwards.
The notes used a skyscraper analogy for this. Walk me through it.
Okay. Imagine a giant skyscraper built right on the equator of the Earth, and the Earth is rotating.
Okay, I'm picturing it. A massive skyscraper rotating toward me over the horizon.
As that skyscraper rotates over the horizon coming toward you, what part of the building do you see first?
I see the top of the tower first, the antenna on the roof.
Right. And then, a little while later, as it keeps rotating, you see the middle floors, and finally, you see the lobby down at ground level.
Right. Because the Earth is curved, the top of the tower peaks over the horizon before the base does.
Exactly. Now, apply that exact same logic to the sun. A sunspot is at the ground level, the surface, or photosphere. But above that sunspot, extending high up into the solar atmosphere, are giant loops of glowing magnetic plasma. That's the top of the skyscraper, the corona.
So as the sun rotates, we should logically see the loops in the atmosphere before we see the actual spot on the surface.
Precisely. And that is exactly what the SDO instruments see. We see the ultraviolet signal, which represents the high loops, rise in intensity before we see the visible light signal, the spot, dip. There is a clearly measurable time lag between the two signals.
That is fascinating. We are literally measuring the rotation of a three-dimensional structure.
And here is why it matters so much for distant stars. When we look at a star 100 light years away, we can't see the loops. We can't see the spot. We just see lines on a graph. But if we observe that the UV light from that star gets bright a few hours before the visible light dims,
we can calculate how tall the skyscraper is.
Bingo. We can estimate the physical height of the magnetic loops on a star we can't even resolve into a picture just by measuring the time lag between the different colors of light arriving at our telescopes.
That is incredible. It's like hearing a thunderclap and counting the seconds to estimate the distance of the storm, but we're doing it for stellar architecture across the galaxy.
That is a perfect analogy. We are decoding the 3D structure of a star from a flat 1D signal.
Okay, let's move to the mystery of the dimming light. Because usually when we talk about activity on the sun flares, heating, magnetism, we talk about things getting brighter. More energy means more light, right? But the data showed something really counterintuitive in a specific wavelength.
Yes. This was a real puzzle for a while. It happened specifically in the AIA 171 angstrom channel.
Remind us again what 171 angstroms represents in this context.
It corresponds to iron 9, iron atoms that have lost 8 of their electrons. This specific state happens when the gas is at a temperature of about 1 million degrees Kelvin.
1 million degrees, which, shockingly, in solar physics is considered just warm.
Correct. It's the warm corona. Now, you would naturally expect that when a new magnetic active region appears, it would pump energy into the gas, making it hotter and brighter in all wavelengths.
Sure. You heat it up, it glows more. That's how fire works.
But in the 171 channel, the area around the active region often gets darker. It actually dims. It creates a temporary hole in the light.
Why? Is it cooling down somehow? Is the energy disappearing?
No, it's getting too hot.
Too hot? How does getting hotter make something turn dark?
Think of the AIA channel like a very narrow window. It is only looking for warm 1 million degree gas. If you take that gas and you suddenly heat it up to 3 million degrees...
the iron atoms lose even more electrons.
Exactly. The iron 9 gets further ionized and becomes iron 12 or iron 15. It physically changes state. And because it's no longer iron 9, it becomes completely invisible to the 171 channel's filter.
Ah, I see. It's like a radio station. The channel is tuned exactly to 101.5 FM. If the signal shifts up to 105.9 FM, the radio just goes silent.
Perfect way to put it. The energy didn't disappear, it just shifted out of the passband. It graduated to a higher energy class. So when we see a sudden dimming in the warm corona, it's actually a definitive sign of intense superheating.
It's a false negative, or rather, a negative signal that actually proves a massive positive event.
Exactly. And again, this acts as a crucial fingerprint. If we see a distant star suddenly go dim in this specific UV band, we know it's not because the star is dying or cooling off, it's because the atmosphere is being flash heated to X-ray temperatures.
Which brings us perfectly to the universal rules of heating. Because this heating question, why the atmosphere is so incredibly hot, is a huge deal in astronomy, right?
Yeah.
I remember learning in school that the sun's surface is about 6,000 degrees, but the atmosphere above it is millions of degrees.
That is the coronal heating problem. It's one of the classic enduring mysteries of astrophysics. It completely violates everyday common sense. It's like walking away from a hot campfire and finding that as you get farther away, the air somehow gets hotter and hotter.
Right. If the core of the star is the heat source, it should logically get cooler as you move outward into space.
Exactly. So something else must be mechanically transporting energy from the surface up into the high atmosphere and dumping it there. And the SDO data has helped us establish universal scaling laws to try and understand this process.
Universal scaling laws. That sounds like a commandment written in stone.
It essentially is a cosmic rulebook. The researchers, specifically Toriyumi and Araputian in their 2022 paper, compared two fundamental things: magnetic flux and irradiance.
So measuring how much magnetism do we have on the surface versus how much light are we getting out of the atmosphere.
Right. And they found a strict mathematical relationship, a power law. And the amazing thing is it holds true for our sun, but it also holds true for young stars, old stars, G-type dwarfs, K-type dwarfs. It seems to be a universal rule across the entire galaxy.
Okay, let's unpack the efficiency part of this law. Because the research mentions superlinear and sublinear relationships. Those are dense math terms. Let's translate them for the listener.
Let's use a volume knob analogy. Imagine the magnetic flux on the surface is the volume knob on your stereo receiver, and the irradiance, the X-ray brightness, is the actual sound coming out of the speakers in your room.
Okay, I follow. So if I turn the volume knob from a 1 to a 2, do I get double the sound?
That entirely depends on which layer of the solar atmosphere you are listening to. If you are looking at the chromosphere, which is the lower atmosphere just above the surface, the relationship is sublinear.
Sublinear, so the slope of the graph is gentle.
Right. You turn the magnetic volume knob from a 1 all the way to a 10, but the brightness only goes from a 1 to a 5. It's very inefficient. You have to pump in a massive amount of magnetism to get just a little bit of extra heating.
Okay, makes sense. What about the corona then? The super hot outer layer.
Up there, it is super linear. The slope is incredibly steep. You turn the magnetic knob just a tiny, tiny bit, and the X-ray volume blasts out the windows and deafens you.
So the corona is basically a drama queen. It severely overreacts to magnetism.
That is a very scientifically accurate way to put it, honestly. The heating mechanism in the corona is incredibly efficient. A very small increase in magnetic flux leads to a massive, disproportional explosion of X-ray and extreme UV light.
Why the drastic difference? Why is the chromosphere so chill and the corona so hyperreactive?
That is where the current debate lies in the field. But the scaling laws give us major clues. It strongly suggests that the actual physical mechanism of heating must change depending on the altitude. In the lower atmosphere, the thick chromosphere, it might be something called wave dissipation.
Like physical friction.
Sort of. Imagine violently shaking a heavy rope. The waves travel up the length of the rope. As those magnetic waves travel upward through the thick, dense lower atmosphere, they lose energy slowly through friction, heating the surrounding gas.
And in the corona, it's too thin for that.
Right, the corona is almost a vacuum. So in the corona, the leading theory is nanoflares.
Tiny explosions.
Billions of them. Tiny, completely undetectable magnetic reconnections happening constantly all over the star. Because the magnetic field is so utterly dominant up there, these tiny snaps release huge amounts of stored energy, flash heating the plasma almost instantly.
So the SDO data is basically helping us figure out which heating engine is running at which specific altitude above the star.
Exactly. And because these scaling laws are universal, we can safely assume this same process is happening on every other star out there, which allows us to do something really cool. We can essentially travel through time.
Traveling through time. This is genuinely my favorite part of the research we're exploring today. Because the sun wasn't always this calm, middle-aged, respectable star we see today.
No, it wasn't. The sun used to be a teenager, and like many teenagers, it was wild, highly energetic, and frankly, a little dangerous to be around.
Stellar evolution is fascinating. Remind us how a typical star ages.
When stars exactly like our sun are first born, they spin very, very fast. They conserve the angular momentum from the giant collapsing gas cloud they formed from.
Just like an ice skater pulling their arms in to spin faster.
Exactly the same physics. And because they spin so fast, their internal dynamo, the swirling engine of liquid plasma that creates the magnetic field, works in absolute overdrive. Fast spin equals massive, chaotic magnetism.
So a young sun is just a magnetic monster.
An absolute monster. It would have been covered in giant star spots, blasting out terrifying super flares every other day. But as stars age, they naturally slow down. They lose angular momentum constantly through their solar wind blowing out into space. It acts like a slow magnetic brake.
This process is called Szymanek's law, right?
Yes. The older a star gets, the slower it spins and the magnetically quieter it becomes. Our sun is currently about 4.6 billion years old. It rotates once a month. It's firmly in its quiet, settling down phase.
But astronomers want to know what the sun was like 4 billion years ago, right when life was just starting to form on Earth. Obviously, we can't build a time machine and go back.
We can't. But thanks to these universal scaling laws we just talked about, we can look at other stars out in the galaxy that are exactly like the sun, but younger.
The young suns.
Precisely. For example, we look at a star called E.K. Draconis. It has the exact same mass as our sun, the same chemical composition, but it's only 100 million years old. On a cosmic scale, it's an infant, so it spins much, much faster.
And because we know the scaling laws work universally across all these stars, we can apply the rules we learned from staring at our own sun with SDO directly to E.K. Draconis.
Yes. We measure E.K. Draconis' magnetic flux. We plug that number into the mathematical equation we derived from our sun, and we can accurately model its entire atmosphere. We verified that the physics is exactly the same. The same equations that describe a small, everyday solar flare on our sun today perfectly describe the massive apocalyptic super flares happening on E.K. Draconis.
That is profound. So by pointing our telescopes at a star 100 light years away, we're actually looking into a mirror reflecting our own solar system's past.
We are seeing the exact harsh environment that the early Earth grew up in. And let me tell you, it was a very violent neighborhood. The young sun was relentlessly blasting the early Earth with X-rays and UV radiation at levels hundreds or even thousands of times higher than what we experience today.
It's a miracle life survived at all under that bombardment. Which brings us to the real stakes of all this research. It's not just about historical curiosity. It's about the search for life right now in the galaxy, the invisible danger to exoplanets.
This is where the rubber really meets the road for modern astronomy. We are finding thousands of planets orbiting other stars, exoplanets. And the ultimate holy grail of astronomy right now is to find a planet that is truly habitable.
An Earth 2.0.
Right. But to know if a rocky planet is habitable, you need to know if it has an atmosphere. You can be at the perfect distance from the Goldilocks zone for liquid water, but if you don't have an air blanket, you're just a barren, freezing rock.
And the biggest enemy of a planetary atmosphere is the host star itself.
Specifically, the star's extreme ultraviolet, or EUV, radiation.
Why is EUV the main villain here? What does it do?
EUV photons carry a massive amount of energy. When they hit the upper atmosphere of a planet, they violently heat up the gas. If they heat it up enough, the gas molecules start moving so fast, they actually reach escape velocity and break free of the planet's gravity. They literally boil away into deep space.
This is exactly what happened to Mars, isn't it?
Largely, yes. Mars's core cooled, it lost its protective magnetic shield, and then the solar wind and the sun's EUV radiation slowly stripped its thick atmosphere away over billions of years. So if we want to know if a distant exoplanet has air to breathe, we need to know exactly how much EUV its host star is hitting it with.
Okay, so that seems straightforward. Let's just point our telescopes at the star and measure the EUV output.
We can't.
Why not? We have the James Webb Space Telescope, we have Hubble, we have the best tech in history.
It's what we call the observation barrier. The vast space between stars isn't actually empty. It's filled with the interstellar medium, a very thin, sprawling fog of hydrogen and helium gas.
And hydrogen loves to absorb ultraviolet light.
It absolutely eats it. It absorbs it completely. From our vantage point here on Earth, The EUV signal of distant stars is totally invisible. It gets entirely blocked by the interstellar fog before it ever reaches our telescopes. We are completely blind to the very thing that determines habitability.
That sounds like a frustrating dead end for astronomers. We desperately need the data, but the universe is physically hiding it from us.
It was a dead end for a long time, until researchers, specifically Namakata and his team in a recent paper, figured out how to utilize the solar scaling laws to bypass the fog entirely.
Using the Rosetta Stone again.
Exactly. Here is the brilliant trick. We cannot see the EUV light coming from the star, but we can see other things. Specifically, we can easily see the calcium Takake line.
Calcium, like in milk.
Same element, yes. It's a very specific wavelength of violet light emitted by ionized calcium atoms glowing in the star's lower atmosphere. And crucially, the interstellar medium does not block calcium light. It punches right through the fog and reaches our telescopes loud and clear.
Okay, so we can perfectly measure the calcium output of a distant star.
Right. Now, we turn back to our Rosetta Stone. We look at a decade of SDO data for our own sun, and we ask a simple question. Hey, historically, every time the sun emitted this specific amount of calcium light, exactly how much EUV was it spitting out at the exact same time?
We find the mathematical correlation between the two.
We build a highly accurate calibration curve. We find that calcium emissions and EUV emissions are tightly predictably linked. If the calcium signal goes up, the EUV signal goes up by a knowable amount.
So we use our sun to create a universal conversion formula.
Exactly. We cheat the system. We take the visible calcium measurement from the distant star, which we can easily see. We plug it into the solar equation we derived, and we mathematically reconstruct the entirely invisible EUV spectrum.
We fill in the blank. We basically reconstruct the crime scene using proxy evidence.
We can effectively say, with high confidence, based on this star's calcium signal today, it must be emitting exactly this much EUV radiation right now.
And that final number tells us if the planet orbiting it is a nice, lush place to visit or just a radiated, airless rock.
Exactly. This breakthrough allows us to realistically model the atmospheres of Earth-like planets around other stars for the first time. We can predict if a planet has been completely stripped bare over 1 billion years, or if it might still have oceans of water and breathable air. All of it is based on math derived directly from staring at our own sun.
That perfectly connects everything we've talked about. We started with a camera just looking at our local sun, and we ended up predicting the weather on alien worlds trillions of miles away.
That is the true power of the solar-stellar connection. You simply cannot understand the distant universe without first deeply understanding the local one.
So let's wrap this up. We have covered a massive amount of ground today.
We really have. It's been quite a journey, from the very surface of the sun all the way to the edge of the galaxy.
We started with the SDO, the ultimate solar camera. We learned that it's not just taking pretty pictures, it's physically mapping invisible magnetism with HMI and peeling back the thermal onion of the atmosphere using AIA.
We discussed how clever scientists downgrade that gorgeous HD data to sun as a star data, creating a functional dictionary to translate the blurry, pixelated signals of distant stars.
We solved the mystery of the faculae, discovering why stars look brighter when sunspots are near the edge because of that crazy hot wall effect.
We looked at the rotating skyscraper analogy, using time lags between UV and visible light to physically measure the 3D height of magnetic loops that are light years away from us. And we explained why a sudden dimming in the corona is actually a terrifying sign of extreme superheating.
We walked through the universal scaling laws using the volume knob analogy, how the corona is superlinear and highly efficient at heating, while the lower chromosphere is sublinear and stubborn.
And finally, we saw how that intricate math lets us see the completely invisible, using calcium proxies to reconstruct the deadly EUV radiation that ultimately dictates the fate of every exoplanet out there.
It really firmly validates the idea of the sun as a cosmic Rosetta Stone.
It really does. It kind of changes your whole philosophy a bit when you look up. The sun is so much more than just our life giver. It is our translator. Without the sun acting as our baseline, the rest of the universe would be a dark, completely confusing place. We would see all those little points of light in the night sky, but we wouldn't understand a single word of the language they are speaking. The sun teaches us the fundamental grammar of the cosmos.
That's a beautiful way to put it. We are incredibly lucky to have such a detailed, accessible textbook right next door.
We are. And here is a final thought I want to leave you with today.
Let's hear it.
We constantly call other stars sun-like. Astronomers use that term all the time. We look for sun-like stars specifically to find Earth-like planets. But as we discussed today, even our own sun hasn't always been sun-like. It was once a raging monster, and billions of years from now, it will eventually swell into a massive red giant. When we look at the night sky, we aren't just looking at a random collection of different objects. We are actually looking at a sprawling photo album of our own life.
A timeline of our own existence.
Exactly. Every star out there is a snapshot of our own distant past or our inevitable future. By studying violent young stars like E.K. Draconis, we vividly see our own birth. By studying old, dying stars, we clearly see our own end. We're really just studying ourselves.
Man, that is deep. I'm going to be thinking about that next time I put on a pair of sunglasses. I'm not just blocking the glare, I'm blocking out the deepest secrets of the universe.
Well, maybe let a little bit of the secret in from time to time. Just please don't stare directly at it.
Sound advice. Thank you all for joining us on this exploration into the Rosetta Stone star. Keep looking up.
And keep asking questions.
See you next time.